Hello and welcome back. In the last episode, we calculated the density of every particle. That gives us a number for how crowded each particle is. But a number on its own doesn't move anything, of course. First, we need to calculate the pressure. And in this episode, we are going to do this. Four things I'm going to talk about in this episode. The first one is what an equation of state is, the Tait equation and its three constants. Then how we can write it into the density loop, and then why the pressure should be clamped to 0. A small recap. In the first episode, in the first real episode, I talked about what SPH is, then the kernels and the poly 6 kernel. Last episode, I talked about calculating density, and in this episode, we are going to get the pressure and the equation of state going. Okay, so here are two particle sets. On the left, the neighbors sit at normal spacing, and on the right, the same neighbors are closer to the center. The middle particle hasn't moved, and the radius is the same. But the density is higher. You can see that right there. The number underneath is about twice as large. The usual thing is water resists that, so compress it and it pushes back, all right? So, and the push is pressure. So we need two things, a density that counts as normal and a rule that turns the difference from normal into pressure, right? And the normal value is called rest density. The rule is the subject of this episode. Okay, so what is an equation of state? The rule is called like that. It takes one number and returns one number, and this is typically density in and pressure out. An incompressible solver calculates a pressure field that cancels the compression exactly, right? That's really accurate. Usually there are commercial solvers where it's really important to have super accurate outcomes, and those are of course not real time. They can take hours or even days, so till you get a simulation going. And we are focusing on the real-time simulations, so we have to do some cheaty ways. An incompressible solver calculates. It's really the incompressible solver is really accurate but really expensive. Well, if you have an incompressible solver which is super accurate, it's usually super expensive too. And we do it in the cheap way. We let the fluid compress a little, measure how much, and calculate the pressure from that. And this is called weakly compressible SPH. There's also a paper called like this. There are two papers which are actually quite the same, or are the same. This is the weakly compressible SPH, and then the other one I mentioned in the last episode. I always forget the name of it, but it is in the description, or I will put it on the screen right now. And the fluid basically compresses slightly, and the simulation, then we are able to run it in real time. The simplest rule is pretty straight. Take the density, subtract the rest density, multiply it by a constant, and that's it. That works, and it's getting used pretty often. But there's also a better one, and the two are easier to understand next to each other. So we're gonna take a look what is the difference between those two methods, between the Tait equation and the linear equation. So let's continue with the Tait equation first. This is the Tait equation. Pressure is a constant times the density ratio to the power of gamma minus 1. It has three constants. The first is the rest density. The density we treat as normal. This one is easy to misunderstand though. It isn't measured, it isn't a measurement of water. It's a value chosen to match our particle spacing, right? Change the spacing or the interaction radius, and the density will change too. And so the rest density has to change with it. It is a setting basically. The second one is gamma. This is the exponent. And for this exponent, well, there's a magic number I'm using. I think I'm not 100% sure, but I think the paper uses it too, and the number is 7. This is usually a good constant for water, and gamma basically determines the shape of the curve we will see soon. The third one is K. This is the stiffness. It scales the result. A larger K gives a stronger response to the same compression, right? It corresponds to the speed of sound in the fluid. So how fast the pressure travels through the whole fluid, basically. The ratio in the middle is the density divided by the rest density. At rest density, the ratio is 1. And 1 to the power of 7 is 1. And 1 minus 1 is 0, meaning a particle that isn't compressed has no pressure. Let's see how the Tait equation and the linear equation look together in a graph. We can see here, this is the linear equation to calculate the pressure. You will see this equation in the paper. I think it's particle simulation for interactive applications. As I said, I'm not quite sure. I always forget the name of that paper. It's in the description anyways. This is the linear equation from this one, and in comparison to the Tait equation, it looks like this. And you can see that the pressure increases way higher when the particles are more clamped together, right? And for the Tait equation, this is coming from gamma. 7 is a high power, so a small amount of compression produces a large pressure. The fluid, it still compresses, but a little bit less. And it returns the rest density also pretty quickly. And the result behaves like a wet liquid rather than a gas. So, meaning if you use the linear equation, you probably have more like a gassy fluid. If you use the Tait equation, then your whole simulation will look immediately different. We will also take a look at this when we are doing the integration and the gravity part. We will see the difference then too. And yeah, then we have one more thing to think about, and this is clamping to 0. Below the rest density, the curve goes under or below 0, as you can see in the graph, and the negative pressure is a pull rather than a push, right? So in a real liquid, yeah, might happen. In a particle simulation, this causes a specific failure. A particle that's too spread out gets a negative pressure and pulls its neighbors towards it. We will check this one too. And the space around it becomes emptier, so those neighbors pull as well, and the fluid separates into clumps, which with large gaps between them, and this is also kind of a tensile instability. You will hear this here and there, and yeah. The fix is really simple. A negative pressure, we will just set it to 0, and that's it. A particle that's too spread out doesn't push or doesn't pull, right? And this doesn't remove cohesion from the simulation. Cohesion comes from surface tension, so which is a separate force, and we will add this later in the series. But it just doesn't come from the pressure term. That's what it means. Okay, so let's jump to the code. First, I want to show you the linear equation again. Same equation of state we just had. Pressure is the density minus the rest density times a constant K, and this is the linear one, and this is what we are comparing against. We will implement the Tait equation, and you can see the right there on the bottom right, and this is the one we are writing. The constants, the constant in front, then the density divided by the rest density to the power of gamma minus 1 at rest density. That bracket is 0, so a particle that is not squeezed has no pressure. So let's add the rest density. This one is 0.003. Then the stiffness, I set it to 2, and then the gamma. I will set this one to 7. And now our method does 2 jobs now, so it gets a new name. We will add the word pressure to the end of compute density. And of course, we have to change the name in the update method too to compute density pressure. So let's do that. And then we can start implementing the Tait equation. For this, we will create a new variable called pressure, and then we will calculate the first term of the equation. This is just the stiffness, the K constant, times the rest density divided by the gamma. And then we can add the rest of the equation. This is just using math.pow multiplied the density divided by the rest density, and then by the power of the gamma, and then all the stuff minus 1, and this is the Tait equation. We still have to do one step though. We're not done yet. We have to clamp the pressure, because a negative pressure would pull neighbors instead of pushing them away, and then the fluid would just break into clumps. And we can do that with just an if pressure is smaller than 0, then you say pressure is 0, and this is everything we need. Then we will save the pressure to the particle, and this field has been 0 since the first episode, and now it actually holds a real value. And this is everything. We are now calculating the pressure. If you run the simulation now, you won't see anything. You still see the square, but we have now pressure going on, and we are set for the next episode. We will see particles moving when we do the integration part. And this is everything for this episode. In the next episode, we will calculate the gradient of the pressure. So we will calculate the vectors we need to push the particles apart. And thank you very much for watching, and I hope I see you in the next episode. Have a nice day, and bye bye.